Okay, let's try to create a design which explains the uh, thermal simulation, electrical thermal simulation using an example. So for that, we start the design using the layout editor tool, that is Blueprint. So we create multiple layers. So we create some 3 layers. So we created different layers. Okay, so layer 1, 2, and 3. So we click OK. We'll start our design from layer 2. Okay, so layer 2 is what we create now. So let's select rectangle and start entering the coordinates 0, 0 and 2, 200. Another small rectangle, which is 2, 0. A small rectangle here. And now we create another one. It's 4, 0, 17, 160. Okay, so we create this. Let's create another one. So that's 4, 160. 6, 200. So create this. Another set of rectangle we create. So we take the rectangle now. 4, 200. 18, 14. So we can take the mirror image of this. Select this. Then take the mirror image. Then we enter the center point, the reference point, 3, 0 and 3, 100. Press escape to deselect. So we get a mirror image here of the same dimension. So let's create one more rectangle. We take this coordinate rectangle here. We enter these coordinates 14, 212. Then 80, 278. So we can as well take the mirror image of this. So exactly from the center. Uh, so select the rectangle, take the mirror image option, and then start entering the coordinates. So 3, 0, 3, so why I'm taking 3 is this center line where it's pointing the center reference point is coordinate number 3 micrometer. Okay, so based on your reference points, you can take the mirror line coordinates. So now this is done. So let's now create a layer in layer 1. So we zoom this section. And then here we create exactly in the center a small rectangle here. So let's enter the coordinates. So -9, 203, and then -5, 207. So let's keep this in the center so we can move this uh, to a center point. So again, I take the mirror image of this. 3, 0, 3, 100. So on the other side, it is created. So one more rectangle needs to be done. So here keeping 1 as the coordinate points. So this represents 1, 2, 5, 10 represents the distance between each points here. So I take this option and then draw a rectangle by a freehand drawing. Okay, and then we select. You can set the dimensions here as well. So we set the coordinate point to be rounded off to 40. So I can round this off to 250. So now we have drawn a rectangle by a freehand drawing diagram. So we can adjust the coordinates using the mouse option. So here you are aware of how to enter the coordinates, so you can do it, but here I've done a freehand drawing kind of a rectangle. So to maintain the same dimension, I'm taking the mirror line again, 3, 0, enter, 3, 100. So escape. So I have created this. So now I formed a layer 1, a layer 2, and now I come back to layer 3. So now I have formed the layer 1, layer 2. Now let's draw something on layer 3. So on layer 3, we take the rectangle again. So exactly repeat the rectangle as it is on this diagram. So it's the same set of dimensions. So now we have completed it. So let's see the layer fill. So we have created something like this. Okay, so let's save this. So let's exit blueprint module. So I come back to the home screen. So in 3D Builder, I import this design, mesh, auto mesh, Manhattan. So I'm selecting this file and browsing it through. So here we have 3 layers, and since we have not defined any thickness in the layout, so here by default everything is 1 micrometer. Okay, so let's for instance increase this to about 10 micrometers, 10 micrometers, further 10 micrometers. So I can define your thickness based on your requirement. So some more settings that we shall do here is Let's change the entity of each layer. So let's save this file. So I'll export this file to the analysis module. So we get this file here. Let's try to do some settings. So let's do some settings here. So we select thermal electrical thermal stress. We select the material properties. So to keeping simple, so I'll assign everything to be silicon 100. We are done with the material properties. Then we go to heat convection. So we need to set the ambient temperature. So hence we select this option. So fill up coefficient 1 and then 25 being the room temperature. 1, 25. So everything is set to room temperature. So we'll go to loads, voltage, entity. Here we select 0 for one, and for another I enter 10 volts. So we have set, then we can go to boundary conditions, then we can fix the walls. Let's fix the boundary conditions. We go to fixed and we select this option and we fix all the four pads, which are two in the top, two at the bottom. So be careful while selecting the boundary conditions. Don't click on the geometry to rotate. So click somewhere outside the area. So in the event if you click something on the geometry while rotating the structure, that face will get selected. So in that event it happens, don't click OK, click cancel. Now we'll set the mesh. So mesh, I'll keep or maintain a very coarse mesh. So let's do the analysis. Now that the simulation is complete, so we can check the results. So we can go to results and see the displacement that's happening. So we can also see the stress distribution. Due to the displacement that is happening here. And also the temperature distribution. Can be seen. So more of a graphical oriented results can also be seen. So for that we can go to post-process for visualities, which I've already done. Once this is complete, so we go to open in visualities. So it will ask us to open the dump file. So select any one of them and then click OK. So here too we get all the results that we saw. All the displacements in different directions, stress components. So if the temperature distribution. So any contours can also be drawn here. Ambient temperature is only 25 degrees, so it's an increase of up to 28 for the voltage applied. So naturally there is a not much of gradient as seen here. So we can see the animation as well. Say we consider X displacement, so we can get the animation. So we can increase the deformation scale so that we get the animation as well. So we can save the animation here, export to AVI file. So I'll not save this file. So this is how we can do a joule heating effect simulation on IntelliSuite. That's how we can do a joule heating. So this is how we can do a joule heating effect simulation on the tool. So here, in case if there is the primary key, in this simulation, the primary key in this simulation, the key factor is the resistivity of the material. So that can always be changed here for the specific material that we wish to use. So we can change its material. So let's do one simulation with the change in resistivity. So we'll increase it to 10 ohm. We will increase it to 10 ohm centimeter. So clean up the previous analysis and then redo the analysis again. So there is a change in temperature. Now let's perform a dynamic simulation. Go to settings, so we select dynamic, thermoelectrical transient, large displacement simulation. We'll run the simulation for 2 seconds with the 20 number of increment. So here increment can be less than 1000, but more the number of increments we increase, there is a substantial increase in the simulation time. So in the interest of time, so we'll retain it as 20. So we click apply, okay. The material properties has already been assigned. So let's go to load, voltage. So let's perform a dynamic simulation here. The dynamic is selected. Thermal electrical thermal stress is selected here. Large displacement with 2 and 20 as the increment number. We click apply, OK. Material properties have already been assigned in the static simulation, so we retain the same. So we go to loads, voltage. So heat convections remains the same. It's the ambient condition of the device. So here we go to load, periodic first. Okay, and then go to voltage, phase. So we set the voltage here. So this is equal to the expression. So insert these values in this expression. So we get the appropriate periodic voltage that you're feeding in. So based on these value, so this is the value that we get. So we click OK to this, and then we go to loads. We remove this periodic then go to load voltage, phase. So we select the other phase. So here we are applying a potential. So naturally we have to apply 0 volts as a reference. So we click to this. Okay. So now we are done. So boundaries are fixed in the previous simulation. So we retain the same mesh analysis. So let's do the analysis. So once the analysis is complete, so we can see the displacements X, Y, and Z. So we can see the temperature distribution. The speciality of purpose of running a dynamic simulation, a time-based simulation, is because we want to see how the temperature distribution is happening with respect to time. So for that, we go to results, we select temperature. So the required data has to appear in the legend form, and then go to results, and then go to node curve on magnitude. So wherever we wish to plot the data, so we can click on that point, so we get the plot. So time versus temperature. Let me push this aside. So with 20 number of data points, so we get this value. In case if we require a smooth curve, increase the number of data points. So here same is the case at all points. It's only the value that keeps changing with respect to time. Okay, so this is how we do a dynamic simulation. Thank you. The loads can also be tabular based. So if we select tabular and then go to load, voltage, phase, and then select this phase, so we can enter this value. So enter unit number 3 and then double click on unit 2, and then we can feed these values. So here we are giving a time dependent voltage. So why have I selected 0.1 here? This is linked to the simulation setting data. So let's look at it. So in simulation setting, so 2 is the time period, meaning to say that for 2 seconds, the simulation will run with 20 number of increments. So 2 divided by 20 is 0.1. So from 0.1 to 2 seconds, the simulation will be carried out. So if we make this as 200, the simulation starts from 0.01 to 2 seconds. So in that case, we will have to edit this value as 0.01 up to 2 seconds. Okay, so we have to enter this value. So to keep it simple, let's go back to, in the interest of time, so let's keep it as 20 itself and then run the simulation. So I clean up the previous analysis. Let's look at the results now. Go to results, temperature distribution. So we see the temperature distribution. To plot the data, we can go to node curve, magnitude, click on the area that we wanted. So when we apply a static voltage, so this is how the temperature rise will happen with respect to time. So for this example, so you can change the resistivity value and then plan to get the appropriate plot. So across the geometry, we can get this plot. So we can get the displacement plot as well. So for that, we have to enable the results of displacement and then go to results, node curve, magnitude, and then click wherever we wish to. So we get the displacement at that point. So this is how we can do a dynamic simulation or time-based simulation for joule heating example. Thank you.